Euler showed that three coordinates are necessary to describe a general rotation. And these coordinates are called the Euler angles. To show how Euler angles work, I want you to think about three successive rotations. The first rotation going from frame A to frame B, the second rotation going from B to C, and the third going from C to D. The key idea behind Euler angles is that if I want to describe the rotation A to D, I can break it up into three successive rotations, A to B, B to C, and then C to D. And you do this by simply multiplying the intermediate rotations. You take the rotation from B to A, and then C to B, and then D to C, and you end up on the left-hand side with a rotation that goes from D to A. So in this picture, you see that the first rotation about A1 is through the angle psi. It's a rotation about the x-axis, and that allows you to get to B1, B2, B3. The second rotation is about the vector B2, and that gets you to C1, C2, and C3. That second rotation is through the angle phi. And then finally the third rotation, which is about the vector C3, and that's through the angle theta. So by simply multiplying rotations about the x-axis through psi, the y-axis through phi, and the z-axis through theta, you end up getting the net rotation, which is from frame A to frame D. Again, you want to remember that the nomenclature here refers both to displacements and to transformations. So if I look at a rotation with a superscript A and a subscript D, it serves two purposes. It can transform vectors written in terms of D1, D2, D3 into a vector whose components are written in terms of A1, A2, A3. It can also refer to the fact that a rigid body has been displaced from its initial orientation at frame A into its new orientation at frame D. The three angles that you see here are roll, pitch, and yaw angles. Imagine a vehicle whose axis is oriented along A1. The first rotation is a roll rotation. The second rotation is a pitching motion about the second axis, which is B2. The third angle is a yaw rotation, and that is about the third axis, which is C3. Euler said that any rotation can be described by three successive rotations about linearly independent axes. So if you have three Euler angles, like the angles I just described to you, you can deduce from them a 3x3 rotation matrix. The question you want to ask yourself is if the reverse is true. In other words, for every rotation matrix, is there a unique set of Euler angles? In other words, does this map between the three coordinates, the three Euler angles, and the rotation matrix, is this map one-to-one? And the answer is no. It's almost one-to-one, but there are certain points that are analogous to the North Pole and the South Pole on the Earth's surface at which the Euler angles are not well defined. This set of Euler angles is often called the XYZ Euler angles, and that's because the sequence in which these rotation matrices are multiplied relates to a rotation about the x-axis, followed by the y-axis, followed by the z-axis. You can also have other types of Euler angles. This particular one is called the ZYZ Euler angles. So again, the first rotation is about the z-axis. You rotate about the z-axis through phi. And then the second rotation is about the y-axis through theta. And then the third rotation is a rotation about the z-axis through psi. Notice that every rotation occurs about a body fixed axis. Once you complete the first rotation, the second rotation about the y-axis is now about a new y-axis, because the first rotation rotated the original y-axis into a new position. Although you have two rotations about z-axes, the question you have to ask is, are they the same z-axis or different? In other words, are the three axes linearly independent? And you can see that the two z-axes are not collinear, they are independent. If this condition is satisfied, then the three angles are Euler angles, and they can parameterize the set of rotations. Note that if you have an Euler angle that is 0, in this case theta being equal to 0, you might run into problems. So theta equal to 0 would cause the two z-axes to be collinear. As a result, you will not have the condition of linear independence. In other words, the three axes about which you're performing rotations are no longer independent. So theta equal to 0 is analogous to being at the North Pole or the South Pole on the Earth's surface. To explore this further, let's look inside the computations that are involved in going from a rotation matrix to the three Euler angles. I'm assuming I have a known rotation matrix, a set of 9 numbers. I want to recover the three Euler angles, phi, theta, and psi. In order to do this, I can write out the result of the multiplication of the three rotation matrices, the rotation about the z-axis, followed by the rotation about the y-axis, followed by the rotation about the z-axis. The first one through phi, the second one through theta, and the third one through psi. And then I can equate these two. You will see that by equating the 3,3 element in the bottom right-hand corner, if I know R33, I can calculate what theta is. So that equation tells me what theta is. Likewise, if I know what theta is, I can look at the 3,1 element and calculate what psi is. In fact, there's a second equation that also gives me the same information. The 3,2 element also tells me what psi is if I know what theta is. And then finally, the 1,3 element and the 2,3 elements tells me what phi is. Knowing what theta is, I can calculate phi from these equations. If the 3,3 element is non-zero, then we can go ahead and calculate theta. You calculate it by taking the inverse cosine function. Of course, the inverse cosine function has some ambiguity, and because of that, you don't know the sign of theta. It could either be positive or negative. But modulo that ambiguity, you can determine theta. And once you know theta, you can calculate psi and phi using the inverse tangent function. You will notice that we had two pieces of information for both psi and for phi. And because of that, we don't use the standard inverse tangent function. We use something called the A tan 2 function. The A tan 2 function helps us overcome the ambiguity that exists in inverse tangent functions. Unlike the traditional inverse tangent function, which only uses one equation to solve for an angle, here we use the fact that we have two equations for the same angle. The inverse tangent function A tan 2 allows us to do this. You will see from these equations that we have two sets of Euler angles. And this is true for almost all rotation matrices. These equations were derived assuming that the magnitude of R33 is not equal to 1, it's less than 1. So what happens if the magnitude of R33 is equal to 1? It can either be plus 1 or minus 1. In those cases, you can easily see that the angle theta is going to be equal to either 0 or pi. And you have two alternatives. In both these cases, you will see from the grouping of terms that the rotation matrices are functions only of the sum of two angles, phi and psi. In other words, it's impossible to determine either phi or psi uniquely. Given one, you can determine the other, but it's impossible to disambiguate between phi and psi because the groupings only contain terms that combine them. So when R33 is equal to either plus 1 or minus 1, you have infinite set of Euler angles. In most of our work, we use a different set of Euler angles. These are the ZXY Euler angles. And again, they're so called because the three rotation matrices we consider are the rotation about the z-axis through psi, followed by the rotation about the x-axis through phi, and then the rotation of the y-axis through theta. You should be able to verify by multiplying the rotations, you get a rotation matrix that has the form shown in this slide. We've seen for every set of Euler angles, you might have at least two solutions for Euler angles for a given rotation matrix. And at some points, you can have infinite solutions. What you really want is a second set of Euler angles to take care of the points at which you have infinite solutions. So this suggests that you might have many sets of Euler angles that you might want to consider so that you don't have a point at which you have infinite solutions. So the question that's worth asking is, what is the minimum number of sets of Euler angles you need to cover all of the rotation groups?